In this video, we'll solve a couple consumer optimization problems. We'll walk through the general steps and we'll do a couple different examples. We'll do sort of like our general Cobb-Douglas case, which produces those convex indifference curves. And then we'll also do a perfect substitutes and perfect complements example. So in general, when we solve consumer optimization problems, we want to first find the MRS by taking the marginal utilities, although we're going to note that it changes a little bit, maybe is a little bit more simple in the cases of perfect substitutes and complements, as long as you can identify what type of problem you're looking at early. We're going to use our kind of golden rule, our tangency condition here, MRS equals the ratio px over py, to write x in terms of y, and then we can plug into our budget constraint, written in terms of I equals pxx plus pyy. All right, so step one, we need to find the MRS, which is the ratio of the marginal utilities, mux over muy. So marginal utility of with respect to x is going to be the derivative of this function with respect to x, right? So what's going to be constant in there? We've got a y to the 0.7, so that's going to come along, and then we're going to bring the 0.3 down. We'll have 0.3 x to the 0.3 minus 1 will give us a negative 0.7. Right, so we've got 0.3x to the negative 0.7, and then the y to the 0.7 is coming along. So we've got 0.3x to the negative 0.7, y to the 0.7. Need to take our derivative with respect to y. In this case, x to the 0.3 is our constant, so that's coming along. We've got x to the 0.3, and then we're going to do a 0.7. Y to the 0.7 minus 1 is a negative 0.3. All right, so we're going to have 0.7, x to the 0.3, y to the negative 0.3. And if you have any questions on how I got these derivatives or anything, just let me know. So now we take the ratio to find MRS, we divide them, right? We've got our 0.3 over 0.7, and we can combine our x's and y's. X to the negative 0.7 is the same thing as 1 over x to the 0.7, so we can put that down here, make that into an x. We get x to the 0.3 plus x to the 0.7 when we multiply them together. Likewise, 1 over y to the negative 0.3 just equals y to the 0.3, so we can bring that up here, multiply it together. Ultimately, we get 0.3y over 0.7x. Okay, so there is our MRS, and this is the slope of the indifference curves at any point. We want to find the exact point of tangency, which is when this MRS equals the price ratio, px over py. So we can say our MRS, 0.3y over 0.7x, equals price ratio, 2 over 1. And then we can simplify, right? This is 2, multiply each side by 0.7x. We get 0.3y equals 1.4x. And then divide each side by 0.3 to get y equals 4.67x. Once again, if you're struggling with any of the algebra steps, just ask and we can do more practice. Okay, so finally, we want to find our optimal x and y star. So we're going to plug that into the budget constraint. The budget constraint is income equals px times x, so px equals 2. Plus py times y, 1 times y, right? So here is our budget constraint, 100 equals 2x plus y. We also know that y equals 4.67x at our point of tangency. So we can plug in that slope at the point of tangency into our budget constraint to find where they're equal, right? We find x star equals 15. And there's two ways that you could solve from here. I think usually the easier way is just to plug in x or whichever one that you found first back into the budget constraint. So we get 100 equals 2 times x plus y. We can solve for y. Now we have X, we have Y, we can plug that into our utility function, and that is our maximized utility. Okay, one other way you could solve for Y, if you take this optimal rule and then divide each side by 4.67 to get X by itself, then you can go to the budget constraint, sub out X that way, and then you have Y that you can solve for. So either way would work. You just need to get this MRS equals PX over PY, write it as Y in terms of X, and then plug into the budget constraint. Right, I have a more general case here that you can look at your leisure. Maybe it helps a little bit to show some of the algebra steps that are going behind the scenes too. So take a look at that. Right, let's take a look at this minimum function. Right, this minimum function is saying that this is a case of perfect complements. The consumer needs 4T for every C. Right, how do we know that? Well, if we're unsure, we can just plug in some numbers. Right, if we plug in a 4 here and a 1, the minimum of 1 and 0.25 times 4 is 1. Right, what about if we had 5T? Then it would be the minimum of 1 and 1.25, which is still 1. Right, so we need the exact ratio, 4 tires for every car, I guess, is the usual example that we're going for here. Right, so now we know that T equals 4C, and it's worth noting that, take some time to think about at the beginning of the problem, what type of utility function is this? Because if we have this minimum function for perfect complements, we're not going to be able to just go in and start taking derivatives. But what we do know is that T equals 4C. We need exactly 4 times as many tires as we have cars. So if C equals 1, how many tires do we need? 4. All right, so that gets us to this step 2, which is using our MRS equals PX over PY. We didn't really need to use that rule there. We were able to just plug in what we know about the optimal ratio. Right? Given this utility, we know what the optimal ratio of the goods is, so we can simply plug that into our budget constraint. T equals 4C. So if we plug in for T, we get C star equals 2, T star equals 8. Or you could have alternatively plugged in for C and solved for T first. You would have gotten the same thing. Okay, so the key to perfect complements is being able to see what this ratio is that you need. And it's always worth just plugging in some of the numbers just to make sure you have it right. All right, what about a case of perfect substitutes? We did perfect complements. Those are going to be those right angle shaped indifference curves. We want to get to ideally one of the axes of those indifference curves, the highest one possible. Here now we have perfect substitutes. So we take our MRS is the derivative of utility. We need a little calculus here, but it's easier because when the terms are separated like this, you just go term by term. These aren't multiplied together, so we don't have constants that are coming along except for whatever's in this term. All right, so when we take the derivative of this with respect to x, we just get 2. There's no x term over here, so the derivative of this part with respect to x is 0. And when we take the derivative with respect to y, we get 0 plus 3, or just 3. All right, so MUX over MUY is 2/3. What's our price ratio? Our price ratio is 2, and we know that 2/3 is never going to equal 2. So we know we have a corner solution here. Now all that remains is to remember which of the two goods we are going to purchase all of, or spend all of our income on only one good. So in this case, we have a marginal rate of substitution, MUX over MUY, which is too low. We would like, if possible, to increase that MRS. How can we increase MRS? Well, we can buy less X. Buying less X increases the marginal utility of X, so it increases MRS. Or we can buy more Y, which decreases the marginal utility of Y, thereby increasing MUX over MUY, or both. All right, in this case, no matter how much additional Y we buy or less X we buy, they're never going to be equal. So we want to buy additional Y and less X infinitely, or up to the point that we're spending all of our income, which means we spend all $100 on Y. We get 100 divided by 6 of them. Okay, so I also posted some example problems just with the indifference curves and marginal rate of substitution, and then the budget constraint and finding and working with those. Let me know if you have any questions like usual.